Welcome to ilectureonline, and now we're going to try to find the electric field due to a solid disk with charge. So we call that a disk of charge. Notice that we put Q amount of charge on the disk, we divide it by the area, we get what we call the area charge density. So it's the charge placed on the disk divided by the area, or the charge divided by pi r squared. I used r sub naught to indicate the radius of the disk. Now the point over here where we're trying to find the electric field is a distance a away from the disk, and then what we're going to do is, what we're going to do then is take a little ringlet right here and make a representative small little dE caused by the small little ringlet full of charge dq. So that ringlet will have a small little charge dq. Now remember, from the previous video we did find the electric field simply caused by a ring of charge. So we have a ring full of charge, and the electric field right here, we're going to call that the dE, because for this problem it's a small little subset of the total electric field caused by the full disk. But the equation for the charge caused by the little ringlet from last video was equal to K times the charge dQ times the distance to the location from the disk divided by x squared plus a squared to the 3/2 power. The only difference between this and the answer of the previous video is that we now just only have a small amount of dq instead of the total charge on the ring. Now the dq here, how do we find that? Well, the dq is equal to the area charge density times the area of the little ringlet, which we'll call dA. And so this is therefore equal to sigma times the area of the little ringlet is going to be the circumference, which is 2 pi x. X is the distance from the center of the disk to the little ringlet, so that would be 2 pi x for the circumference, times the thickness, which is dx. Notice I used the variable x for the radius of the disk, so not to be confused by the full radius of the disk, and not to be confused by this distance right here. All right, so now we have the value for dq. We can place that into our equation right there. So we can write that dE is equal to K times dQ, and our dQ is sigma times 2 pi x times dx times a divided by x squared plus a squared to the 3/2 power. All right, now we should be ready to integrate, because now to find the total electric field right here, we're going to integrate across all the little ringlets. Remember that the value for dE is going to be horizontally outward, because all the perpendicular components were eliminated by integrating around the whole little ringlet right here. So we only have to worry about the horizontal component, dE, and then if we, of course, integrate across all the little ringlets, we'll get all the sums of dE's added together to get the total electric field. So the total electric field E is going to be the integral of all the little dE's, integrating from x equals 0 to x equal the full radius of the disk. That means we're going to integrate this whole integral right there. So this is equal to the integral from x equals 0 to x equals the radius of the disk times k sigma 2 pi x dx times a, all divided by x squared plus a squared to the 3/2 power. Now in this integral we have a lot of constants. Notice that a is a constant, pi, 2, sigma, and k, they're all constant. They can all come out of the integral. So this is equal to k sigma 2 pi a. And then we have left in the integral, and let's see here, an x dx. And in the denominator we have an x squared plus a squared to the 3/2 power from 0 to r sub naught. So those are the limits of integration. Now this is a fairly straightforward integral, because notice in the denominator we have an x squared plus a squared to some exponent. In the numerator we have an x dx. The differential of the denominator is a 2x dx. So we need a 2 here. That means we need another 2 down here. Now we can go ahead and integrate. So this becomes x squared plus a squared to the minus 3/2 power when we bring it to the numerator. Then when we integrate, we add 1 to the exponent, divide by the new exponent, and this is what we'll end up with then. So the electric field E is equal to all those constants, and notice that these 2's cancel out right there. So we have K sigma pi A, and now we're going to integrate this, and so this now becomes 1 over the quantity x squared plus a squared to the 1/2 power But notice we also have to divide it by the new exponent. The new exponent, when it's a numerator, was a minus 1/2. Divide by minus 1/2. That means divide by minus 1/2 goes over here. That means the 2 goes over here, and the minus goes over here to get rid of that. All right, so now we got the proper result of the integral, and the limits are going to be from 0 to r sub naught. All right, now we have to evaluate that when we plug in the upper limit. Let's see here, let's write it over there. So we still get k. Oh, and by the way, to make this a little bit simpler here, let's write k as 1 over 4 pi epsilon sub naught. That will simplify things a little bit. So we can write k as 1 over 4 pi epsilon sub naught. Then we're left in the numerator with a sigma, 2 pi, and that will cancel out here, and an a. So the reason I did that, because notice then the pi's cancel out, and this 2 will cancel out with that 4 becomes a 2 epsilon sub naught in the denominator. All right, and then when we evaluate this, we end up with minus 1 over, plug in the r sub naught for x, we get r sub naught squared plus a squared to the 1/2 power, and then minus, when we plug in the lower limit, but since we already have a minus there, it becomes plus 1 over, we put a 0 in for x, we get 8 squared to the 1/2 power, or 1 over a. All right, almost done. Now notice if I multiply this a in here, I'll get a minus a over this, and a over a gets me a 1, and I'm going to switch those around because this is positive and this is negative. So then finally I can say that the electric field is equal to, I'm left in the numerator with a sigma, in the denominator with 2 epsilon sub naught times, so a times 1 over a becomes simply 1, minus, because I still have the minus here, so that becomes a divided by the quantity r squared, r sub naught squared, plus a squared to the 1/2 power. And now that gives us the electric field strength at this location due to this charged disk. If I want to make it into a vector, I put a vector symbol here and put the unit vector in the x direction there, and that will then be the electric field to the charged disk. I know that algebraically we can still write this in different forms, but that is one of the more simple forms to leave it as. And again, the goal here was to find the electric field here because of a charged disk. Start out with a small little ringlet of charge. The dq is equal to the area density or area charge density of the disk times the area of the little ringlet, which is the circumference 2 pi x times the thickness dx. That goes in here to the result of the previous video, so the dq becomes equal to this, and then we integrate, because then all we have to do is sum up all the little ringlets to get the full electric field due to the entire disk like that, and that's how we approached it.